Right, as usual, let's record what we have learned in the previous lecture. Um, last, in the last Wednesday, we learned semiconductor, right? And then we know there are three methods to do the excitation of for the semiconductor. That means we want to know how to make semiconductor works. How to make it work means that how do you deliver the conductivity in semiconductor? And there are three methods. The first one is called photon excitation. That's what we learned on Wednesday. And the second one is thermal excitation. We use thermal energy to excite semiconductor to let it work. And the third one is called chemoexcitation. This is what we are going to learn today. We use kind of chemical method to make the semiconductor works. Okay, so I think we all know this, and we know that in the end of the lecture on Wednesday, we know that the thermal energy is kind of a distribution of is a Boltzmann distribution for the molecules. You know, we regard molecules as a kind of individuals. So there's kind of temperature distribution for the molecules in this room, and so these molecules followed by the temperature of these molecules followed by the Boltzmann distribution. Okay, so today we are going to talk about chemoexcitation. Chemoexcitation. Right. So what is chemoexcitation? Imagine this is a silicon or carbon. For example, this is silicon, right? Because silicon is semiconductor. And this is atom of silicon. And then, you know, is sp3 hybridization, right? So you have one silicon, and then this silicon connect to four adjacent silicon atoms, and is bounded using the covalent bond. So imagine if we replace one of these silicon to become a foreign atoms. For example, phosphorus, for example, boron, these kind of different atoms into this. That means the property of this material silicon change because of the foreign atoms, right? And the chemical bond changed. Okay, the energy or the bonding energy or the bond length of this between these two atoms are changed. So chemoexcitation is called it means that the carrier injection by introducing impurities in silicon. Impurity in silicon means what? That we put this in different impurities. You can put different atoms, different type of atoms, as I just told you. Let me give you an example. For example, if you have rice, a portion of rice, you know, you eat rice every day, or just in case, you eat rice every day, you know, if you put sesame, do you know what is sesame? 芝麻 into this rice, that you can regard 芝麻 as a kind of impurity or foreign atoms into this rice. I mean, it's good, right? It's good because it tastes good, tastes better than the plain rice, right? So this dopant, and this impurity we call it dopants, which is good for the rice, or good for you to eat. Okay, but however, if you put you know, something like 小强, you know, if you put 小强 baby 小强 into this cockroach, if you put cockroach, baby cockroach in this portion of rice, what happened? You got sick, right? You don't want to eat rice for the rest of your life, right? Okay, so this is kind of contaminate. It's not good at all. So That is also the baby cockroach is kind of impurity too, right? So for impurity, you have good or you have bad. And today we are going to talk about good impurity, which is we call dopant. So dopant is that the change the composition of the materials. So you put dopants in to replace this silicon carbon, silicon atom, and then the property change, which is good. Okay, changing the composition of material, or we call engineering materials vice chemical change. You know, if you replace this atom, silicon atom to another foreign atoms, chemical bond change in terms of energy, in terms of bond length, right? So it's also we call energy engineered materials. I hope you still remember. Um, you heard a term called band gap engineering. Band gap engineering tell you that you manipulate the band gap by changing the compounds of the semiconductor. Okay, so this is also engineering. So if you put A atoms, B atoms, C atom, foreign atoms into silicon wafer, you also change the property of this silicon crystal, for example. So tailored composition to give a tailored property. So you need to know what kind of property you want, and you design the material. Okay. So what can we change? What can we do for the silicon crystal? So introducing adiovalent impurities is to cause electron donor or electron consumption. Electron uh, electron donation or electron consumption. So this is silicon, right? So you want to change the number of the electrons. Okay, so if you want to have more number of electron, you put arsenic or phosphorus, right? Because this group, the valence electron, there are 4 valence electrons in 14A group, right? So there are 5 valence electrons in the 15 groups in the periodical table. Okay, and there are 3 valence electrons in the 13 group 13, right? So if you want to have electron donation, what do you want? What type of elements you need to put? You need to replace silicon atom here. If you want to have electron donation, you better replace silicon by phosphorus, right? You better replace silicon using arsenic. This is called electron donation. However, if you want to have electron consumption, that means you want to have one electron short, then phosphorus, boron will be the one, because the boron has only 3 electrons in the valence shell, okay, of the atom. So the first case, let's see that arsenic doped silicon and its donor energy band. So this is silicon, for example. It looks this 2-dimensional surface. You take a look of this. It is silicon. So this silicon has 4 valence electrons, and the Johnson silicon also has 4 valence electrons. So in total, this one has 8 valence electrons. This applied to ATEX stability, right? So it's S2P6 ATEX stability. So this silicon is stable. Okay, so now you want to replace this silicon, and this band gap is 1.1 electron volt. You want to replace this silicon to become arsenic. So what happened? You have 1 electron extra. Am I right? Because valence electron, there are 5 valence electrons. So you have one electrons in the valence shell. And where will this electron be? Here or here? And how strong this electron will bond by this arsenic atom? That's the question you want to know. That's the question I want to ask, and then you also want to know. So this is how we call extra electrons and donor. This electron want to attach to anywhere. So what is the energy of these electrons? Energy. So let's go back to the Bohr atomic model. In the very beginning, we know that if we want to calculate the energy of this electron for Bohr model, this electron, basically this electron will be minus 13.6 electron volt. I hope you still remember this number. No problem, right? This is the very basic knowledge you want to know, you need to know. But however, this is not a single electron atom. This equation doesn't apply to this case. So we had to modify this equation. So for example, the modification of the silicon, and also is for solid states. Epsilon 0 become epsilon Si, because dielectric constant of the host crystal, this epsilon 0 has become epsilon Si, and M is the mass has to be modified. We call effective mass of the electron. So if you replace these two, the equation you got is like the energy for this electron is about minus 0.02 electron volt. Wow, compared to minus 13.6 electron volt, this electron only got minus 0.02 electron volt. That means what? All of the electron here will sit in the valence band. However, for this electron, the energy will be what? The energy will be somewhere around here. This is for you to do a simple calculation. Of course, this is a rougher. Number is a rougher number. However, if you do the measurement, the energy for this electron is about minus 0.045. Well, normally you just remember 0.05 electron volt. So the energy of this electron, which is donor, and this electron will sit here. So this is the energy. So for the energy, so the rest of the electron energy and rest of the electrons sit here, and if you want to pump electrons from the valence band to conduction band, you need 1.1 electron volt, right? However, for this donor, how many energy you need to let this electron become a conductor, to make this electron to be a conduction band and to make the electricity? Then the answer is 0.05. So this is much easier, right? This energy is much easier than 1.1 to pump the electron from valence band to a conduction band. And this is great. Why? Because you don't require heavy energy to make the semiconductor to become a conductor. So this is the energy. So, and then next question is how far does the electron goes? Where is this electron? Is it somewhere here? Is that somewhere here? Is it possible to be here, closer to the arsenic compared to the valence electron? No way, right? It must be somewhere far away from this one. Okay, so let's take this example. Arsenic dopant silicon as a nucleus and the arsenic nucleus to the electron distance. So how far can this electron run? Again, let's use the most easy case is the Bohr atomic model. For hydrogen, you only have 1 electron. How far? The answer is 0.53 angstrom, right? I hope you still remember this number. This is important, 0.53 angstrom. Again, you modify dielectric constant, you use modified mass, we call effective mass, and you put this number into this equation, and the answer you found is about 3 nanometer. 3 nanometer. So what's the distance between silicon and silicon? The distance between the silicon and silicon is about 2.35 angstrom. So you have 30 angstroms. What does that mean? This the distance between this and this is about 2.3 angstroms, and this one is about 30 angstroms. So it's very far. You don't know where is this. It's too far. What does that mean? This electron is not controlled by this arsenic atom anymore. So it's very, very far, and then it cannot be controlled. So the energy is required very less to become a free electron and to deliver the electricity, right? Okay. So this is the things that if you introduce arsenic atom to the silicon crystal, you will find out the chemical property changed, the conductivity changed. So let's take a look of the thermal versus the dopant energy. So more dopant atoms enter to the substrate. If I had just the previous slide, I told you that if I just replace one atoms of the silicon to arsenic, right? You have one extra electrons in as a donor, and then the band gap is very, very close to the conduction band. So we have more electrons. If you replace more arsenic, of course you got more free electrons, right? You got more electrons. That means what? You got better conductivity. Okay? So the numbers of the electrons is more. So you got better conductivity. You might say, well, Professor, can I change all? Can I change half? Well, in that case, you won't be a silicon crystal, right? You'll become a compound. The property is completely changed. So normally you don't change all. You just put a dopant. For example, if you have a portion of rice and you put half amount of sesame into this rice, do you call this rice? Do you want to eat? No, you don't, right? You just want to address this rice only, right? By sesame, and it tastes good, but you don't want to have too much sesame. Right, so the number of the electron is equal to the number of the holes plus the number of impurities. And you know the number of the electron in the whole silicon is 0. So this property is all dominated by the numbers of electron for the dopant. Sorry, PANT, dopant. Okay, so the numbers of electron impurity is much more than the numbers of holes in silicon. So electrical properties are essentially loose from the impurities. So now you want to control the electricity or conductivity. It depends on the numbers of these electrons. It not depends on the number of these electrons in the valence band. So this is called intrinsic behavior. You will know that another term called intrinsic behavior. This is extrinsic behavior. Extrinsic behavior means that it's not the property doesn't dominate by its original properties of the silicon, but by the fluorine atoms. This is called extrinsic behavior. So it also depends on dopant dependent. How many dopants? What type of dopants into this silicon? So undoped silicon inhibits intrinsic. So if you have a pure silicon, this property is intrinsic. All the properties are all call intrinsic behavior. And because of the number of the dopant in the numbers of the electron of the dopant is much more than the numbers of the electrons of the silicons for the thermal excitation. Thermal excitation is very little, right? It's 10 out of minus 19, right? 1 out of 10 to minus 19. So the ratio is, the probability is very low. So, the numbers of dopant is much, much higher. So, and then we also know the number of the electron is much more than the numbers of the electron hole. Because you have extra electrons, you don't have hole. So this is what we call supervalent dopant. Supervalent dopant. And this is also called N-type semiconductor. Ladies and gentlemen, I want you to remember this very well. What is N-type semiconductor? N stands for negative type. So if very soon, the next slide, I will show you P-type semiconductor. What is N-type? N stands for negative. Negative means what? You have extra electrons. Extra electron means what? Electron is negative charge, right? Not positive charge. So of course you call negative N-type semiconductor. Okay, so next one is called P-type semiconductor. Okay, P-type normally is what? We put phosphorus, arsenic, then we have 5 valence electrons in this column, and then we have 3 valence electrons in this column. So we use boron. So you replace silicon to boron. We call what? Instead of supervalent, this is called subvalent. Subvalent impurities, boron. So you change this silicon to become boron. As a result, you have extra electron hole here. Again, this is impurity, so this must have a higher energy, right? So this is called hole. We call acceptor. Acceptor means what? This acceptor, this is a hole, so you can ask another electron to fill this hole. Okay, so this hole is called acceptor. So where is the energy of this? Where is the energy of this electron hole? After you do the calculation, you realize this hole is energy of this hole is about 0.05 electron volt in this place. So for the electrons in the valence band, is it easy to make the electron jump to here? It just requires 0.05 electron volt. It's easy, right? How about you don't want electron to jump to here because it's 1.1 electron volt. It's too much energy to consume. Okay? So if you have 1 electron in the valence band, and then you just require very little energy to pump this electron to here. And what happened? Conductivity, if you let electron flow, that means what? Conductivity, electrical conductivity, right? Okay, however, the number of the electron is much, much less than the number of the electron hole. So this is what we call subvalent dopant. And this is what we call P-type semiconductor. P stands for positive. Positive. In contrast of the negative of the electron, this is positive. So we call P-type semiconductor. Okay? Are you okay? Are you with me so far? Yes, right? This is not difficult at all. Hope you remember. So now let's illustrate how hole move. So illustration of the hole movement. For example, if you replace boron to become silicon to become boron, you have an electron hole here, and this valence band, this conduction band. And electron, if you have hole here, electron will move, right? And you have a hole here, electron move. So you have more holes here, so electron will stay here, so you have more electron hole here, so electron move from right to left. So this is how the conductivity takes place. So I have a question for you. So this is called P-type, P-type semiconductor, and the previous one is called N-type semiconductor. So I have a question for you. Have a guess. Which one moves faster? P-type electron in the P-type semiconductor, or electron or hole in the N-type semiconductor? Which one move fast? Hole move fast or electron move fast? Of course, electron, right? Electron is free. Okay, electron is free, so you move fast. Right. So this is a kind of comparison of the semi-excitation versus chemical excitation. You know, for thermal excitation, you need to have enough energy to pump electron again from the valence band to the conduction band. So the band gap is 1.1 electron volt. So this, and if you move the electron from the valence band to the conduction band, this is called thermal excitation. For the silicon, it requires 1.1 electron volt. So unless you melt the silicon crystal to become liquid, otherwise electron doesn't move because the the temperature needs to be very high in order to move the electron from the valence band to the conduction band. However, for the chemo excitation, it doesn't require large energy. So if you have a band here, you can move the donor from here to here. You can move the hole from here. You can move the hole from here, electron from here to here. Okay. So please release by yourself. So after we understand the semiconductor, now the next step is how to use semiconductor to become a transistor. You know, transistor is very simple. It's like, you know, you found it's just like a switch on, switch off. How do you make the transistor? How do you make a device you can switch on and switch off? And switch on, you can regard on as a one. Switch off, you can regard the device as a zero. So it's kind of digital world, 0, 1, 0, 1. You just play 0 and 1. That's it. Okay. So how are you going to do this? Make this device and make it very, 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 very small. That's it. Okay. So there are three giants in United States. They got Nobel Prize, and they were in the Bell Lab in 1947, and they invented a first transistor, and then they got Nobel Prize after 11 years later. Okay, so but it's still too far for you to understand, and we have a lecture in the graduate school. So I will introduce semiconductor to you if you are interested. If you go to the graduate school in this university. Okay, right. So how is silicon wafer? If you have a wafer, you can you might name this wafer as P-type semiconductor as P-type silicon wafer or N-type silicon wafer. So you have P-type and N-type. P-type, N-type means that you just use for P is positive, right? So you use boron. N is phosphorus or arsenic. Okay, it looks like this. It can. Okay, and this is the 111 is crystal orientation. We are going to talk about this in chapter 3. Okay, 100 is also crystal orientation. So this industry is very, very strong in Taiwan, and you know we are proud of this industry in Taiwan because everybody knows Taiwan is very strong in this industry. This is called semiconductor industry, or called VLSI, very large scale in the integration process. So you have a wafer. In the previous slide, you have wafer, which is plan, and you make a very small square. It can be 200 squares. Here we call it chip. Chip. It's not potato chip in McDonald's, okay? It's a chip in semiconductor. So this wafer can be 6-inch, 8-inch, or 12-inch. And in the future, it can be 18-inch, but it's under development. I don't know whether they give up to do the development or not. But anyway, now for the high tech, we use 12-inch. Okay, for example, if we think of this 12-inch, and if you have a micro, this is before process, this is after process. After process, it can be 2,000 processes, 2,000 steps, and to do one by one, And once you finish this, you take this out. It's like 2 times 2 square chip, okay? And if you enlarge this one out, and you will see something like this. This is called MOS. MOS stands for metal oxide semiconductor, MOS. The figure size is less than 100 nanometer. And now the more advanced technology is about what? 3 nanometer in TSMC, right? And we are going to go to the 2 nanometer. And after that is 1.4 nanometer. Very exciting. Okay, so this is the MOS. So how many this transistor in one chip? Do you know how many? How many? 1 billion. 1 billion. Right, so let's think of the integrated circuits and the discrete circuits. This is discrete circuits. When I was young, I played this a lot. Now this is capacitor. This is resistor, and this is transistor. So you only have 3 kind of devices. One is capacitor, transistor, and resistor. Okay, you put these together, and you make it like you can see. But now you have to integrate this all to become very small. As you can see, you can find this kind of, you have chip and put this to become a device. This is CPU, as you know, the CPU. So this is a roadmap for the Intel's process technology. So from MOSFET, this is called metal oxide semiconductor field effect transistor. It become planar FET. Planar FET looks like this, and now it's FinFET. This TSMC use this technology. Samsung use this technology. Gate all around. And TSMC is going to move to this gate all around, right? You know that. Okay, so it become, now it's 7 nanometer, 5 nanometer. If you have a up-to-date iPhone 15, that would be 3 nanometer, 5 nanometer, right? And 3 nanometer technology. And now it's going to move to 2 nanometer, and then very soon it will be 1.4 nanometer technology. Right. Okay, so let me summarize the semiconductor. First of all, you need to know band. Of course, you know the band when you learn magnetic bond. And because of semiconductor, you learn another term called band gap, right? This is band, and this is called band gap. Band gap, band. Okay. For applications, photovoltaic, LED, and also LED, right? For semiconductor, compound semiconductor, you have band gap engineering. And there are 3 ways to excite a semiconductor. One is photon excitation, and using photon excitation, you can measure the band gap of the material. Another one is thermal excitation. chemoexcitation is the one we introduced today, right? Okay. Right. So let's move to another topic called liquid, gas, liquid, and solid. How do you distinguish? How can you tell what kind of properties dominate the gas, liquid, and solid? Okay. So now let's think of the gas, liquid, and solid. So for the oxygen, if we regard oxygen, have you seen oxygen ice? You have liquid or solid oxygen or liquid oxygen. I'm sure you have heard liquid oxygen, and oxygen is in the gas phase, right? There are 21% of oxygen in the air. So you suck oxygen into your body every day, every second. Okay, so the distance between oxygen molecules are very far, and we regard it as a gas. If it's closer, oxygen molecule closer to a certain distance, we regard this phase as a liquid phase. If oxygen molecule pack very well, very close, there's a very little space for oxygen, and we regard it as oxygen ice or oxygen liquid, solid, oxygen solid. So why make this happen? Temperature, right? Temperature. If you have higher temperature, the oxygen is in gas. If you have a medium temperature, the oxygen becomes liquid. If you have very low temperature, oxygen become solid. So that means what? Thermal energy against what? Bonding energy, right? I should say this is kind of physical bond. It's not chemical bond. We already learned chemical bond. They are ionic bond, covalent bond, and metallic bond. These are called chemical bonds. But there are another type of bond called physical bond. And physical bond is against if the physical bond against thermal energy or thermal bond, physical energy, the energy of physical bond against the thermal energy. That means you can form solid, liquid, or gas. Okay? So formation of solid, liquid, or gas is ionic bond. Let's think of can these three primary or chemical bonds can form gas, liquid, or solid. Why? Okay, so the first one, ionic bond compounds, ionic crystal forms. So ionic compound can be regarded as sodium chloride, right? And then magnesium oxide. This is ionic bonding. And this is at room temperature. This can be heavy liquid, solid, or ionic liquid. Ionic liquid. How about covalent bonds, covalent compounds? Covalent compound is the bonding of molecular. For example, methane, sulfur fluoride, chlorine, and H and water. These are gas. This is liquid. So these are all covalent bonds. And the networks like solids, like diamond or silicon. This is covalent bond by being solid. So, and the metallic bond is lithium is solid, mercury is liquid. These are all metallic bonds. So, according to three chemical bonds, you cannot distinguish what kind of bonds form liquid, solid, or gas because ionic bond has solid and liquid. Covalent bond has gas, liquid, and solid. And then metals can be a form of solid or liquid. So you cannot distinguish this. So what kind of phenomena or what kind of force or energy can tell this is related to the gas, liquid, or solid form? That's what we call cohesive forces versus destructive forces. Cohesive forces means what? The bonding energy. And destructive forces means what? Thermal energy. Okay? So let's think of the bonding energy of the substance versus the general thermal energy. General thermal energy means what? The the energies the energy surrounding the object. That's called general thermal energy. So for the ionic crystal, for sodium chloride is about 8.18 electron volt. So the lattice energy is 8.18 electron volt. And how about the room temperature? If it's at room temperature, I hope you still remember room temperature is about 25 Celsius. The energy of the room temperature is about what? 1 out of 40 electron volt, which is about 0.025 electron volt. So when you see this is thermal energy, and this is bonding energy. So seems this energy is not high enough to take this apart, take crystal apart, right? Okay. How about covalent crystals? Another example is diamond. Diamond is 7.4 electron volt. Oh, of course, temperature is not enough. How about molecular? Molecular. This is called sulfur fluoride. Sulfur is in the middle. Fluoride, there are 6 fluoride, fluorine atom. Fluorine atom is, there are 6 fluorine atoms surrounding this sulfur. And this is, if you have this, and this is the gas. These are, we call sulfur fluoride gas. And this is big molecular. And this one, H2O, is small molecular. So you know that hydrogen is very small, atom is very small, oxygen also very small compared to sulfur and fluoride. So this is the atom. Why? Why this is liquid, this is solid? Seems this need to be solid, right? Why this is liquid, this is solid, this is liquid, this is solid. Sorry, this is gas. Gas. Why? So that's why we are here we are talking about intermolecular forces. Intermolecular, we have intramolecular bonding. Intramolecular bonding means this is molecular, and the bonding between atom and atom, this is called intramolecular bonding. And another one is intermolecular force or intermolecular bonding. This and this between is intermolecular. This is intramolecular. Okay? So treat what is going to on inside of the molecules between atoms. And when we talk about ionic bond, ionic bond, mechanical bond, or covalent bond, we are all talking about intramolecular. Okay, so we use electron domain theory. I'm sorry, we skip this topic. Electron domain theory. So this is called primary bond. Primary bonds including, I just told you, ionic bond, covalent bond, and metallic bond. So another force is intermolecular forces. That means determine the state of the aggregation. State of aggregation means what? If aggregation means how close they are. If they are very close, solid. Medium close, liquid. Very far away to each other, gas. Right? This state of aggregation. So solid, liquid, and gas. And this is what we call secondary bond. So primary bond, secondary bond. So there are four types of the intermolecular forces. Between these, there are 4 types. There are 4 types between these bonds. Okay, so section 2.7, secondary bondings. That's what we are going to talk now. And we need to know dipoles. We already learned the dipole, right? And the dipole interaction, that's what we are going to learn now. So there are 4 types. The first one is there are 3 types. The first one is dipole-dipole interaction, or we call permanent dipole bonds. Ladies and gentlemen, these are secondary bonds. Okay, it's not primary bond. Dipole-dipole interaction and dipole-induced dipole. We call polar molecular to induce dipole bonds. And the third one, of course, you understand, is called induced dipole bonds, or we call fluctuating induced dipole bonds. I'll explain this one by one to you for now. Okay, so the secondary bonding, we just quickly talk about this. The secondary bonding is van der Waals, we also call van der Waals force, or physical bonds, are weak in comparison to the primary or chemical one. So the bonding energy is small. Physical bond, the bonding energy of physical bond is smaller than the bonding energy of the chemical bond. So normally the bonding energy is less than 10 kilojoule per mole, which is about 0.1 electron volt. But of course, this is higher than the room temperature, right? 0.025 electron volt. Secondary bonding exists between the virtually all atoms or molecules. It exists, but you ignore it because the thermal energy is much higher. Somehow thermal energy is higher than this, or the primary bond is higher than this. So but it is presents may be obscured if any of the three primary bonds types is present. That means what? If you have primary bonds, you normally regardless of, you normally ignore the secondary bond because this is too weak. Bonding energy too weak. Okay, so now we take a look of the inner gases, stable electron structures. Then normally they are, you can observe this very well because between the inner gas there is no primary bonds because it reach S2 P6 Artex stability, right? So you can see the secondary bond well, or you can observe you can observe secondary bond well using inner gases. Right, the types of the secondary bonds, there are two. The first one is van der Waals bonds. Van der Waals bonds. And inside the van der Waals bonds, there's one special bond called hydrogen bond. Okay, so you need to remember this too. And hydrogen bond actually is a special case of the van der Waals bond. And why we have these bonds? The secondary bonding rises from interaction between dipoles. So first of all, we need to know dipoles, and then we move to the understanding of the secondary bonding. Okay, so dipole interaction, dipole induced dipole. What is dipole? What is induced dipole? So the electrical dipoles exist whenever there is some separation of positive and negative portion of an atom or molecule. For example, you have an atom or you have a molecule, and at that time, or in some cases, there's a kind of separation of positive part and negative part. This is called dipole. So let me give you an example. An induced dipole. What is an induced dipole? For example, this is a molecule, is an atom. So as we know from the atomic model, this is a nucleus inside and there is a electron orbitals surrounding, right? So it's a kind of electrically symmetric atom. Okay. However, if you give this atom some kind of forces, and then something happen, it means that electron doesn't distribute symmetrically. Electron somehow move here more. So we call delta minus and delta plus. That means what? That means we have a dipole. And this is called electron cloud. Electron cloud move something like this. So electron move more. You have more possibility to find electron in this place and less probability to find electron here. So this is called dipole. And we can use sign like this, positive and negative. They can apply in a molecular or in an atom. So now we already know this term called polar molecules. The permanent dipoles moments exist in some molecules by virtue of the asymmetric. Asymmetric means that it's contracts of the symmetric, right? It's called asymmetric arrangements of the positively and negatively charged regions. Such molecules are termed polar molecules. So hydrochloride is a polar molecule because you have dipole, right? The more the electron of the hydrogen will move to the will be closer to the chlorine gas, chlorine atom, and you have positively N in the hydrogen region. You have negative N in the chlorine region. So this is an example of hydrogen chloride. Okay, so permanent dipole rises from a net positive and negative charges that are respectively associated with the hydrogen and the chlorine ends of the hydrochloride molecule. Okay, but in term, this is neutral. Of course, you think that, well, Professor, I have a positive N and negative N in both sides. And then if positive N and negative N get together, it becomes neutral. So in this molecule, this is neutral molecule. Right, secondary bonding forces is the secondary bonding forces rise from what? I just told you, dipole, atomic dipole, or molecular dipoles, right? This is molecular. For example, this is H2O, H2O, H2O. So you have positive N, H2O, right? So this is H2, this is H, this is O. So you have positive N, negative N. You have negative N, positive N. So between positive N and negative N, there's kind of attraction. So this become a dipole. And this dipole and have a force. So this is force, secondary bonding force. And this dipole. So van der Waals bonding between two dipoles. So you have dipole molecular, and van der Waals force between two dipoles. So why they have force between two molecules? Dipole, right? And why they have dipole? Why have a force? Coulombic attraction. Positive, negative. So the bonding results from the Coulombic attraction between the positive end and the negative region of the adjacent one. Adjacent means what? Neighbor, right? They are neighbors. Right. Let me show you here. Example of H2O, negative, positive. Negative, positive. This attraction between each other. Right. So the types of the dipole interaction is that, as we just say, that dipole interaction, polar molecules, and dipole-induced dipole molecules. For example, you have dipole molecules. Between dipole and dipole, you have interaction. This is called dipole-dipole interaction. That's between the polar molecules. How about dipole-induced dipole interaction? That means you have one polar molecule, for example, and then you have an induced dipole. This is an atom, for example, and there's no dipole, but this was induced by this molecule and it become a dipole. So there's an interaction between dipole and induced dipole, and this is called dipole induced dipole interaction. How about induced dipole interaction? This is very interesting. So how come you can have an induced dipole? You can have two induced dipole. The forces are temporary and fluctuating with time. And we are going to talk about this. I don't know whether we have time today or not. Maybe not. We might talk about this next week. But let me start from the first topic. The first topic is dipole interaction, permanent dipole bonds. This is easy. I just want to tell you, let's make example of hydrochloride. The hydrochloride, you have one hydrochloride, and this is the dipole molecule. Right? This is the dipole molecule, and we understand you have the positive end in the hydrogen atom, you have negative end in the chlorine atom, and then assume if you have another hydrochloride which is close enough to another one, and this will be positive end, negative end. And what happened to these two molecules? Interaction, right? And make a secondary bond, and we call van der Waals bond. So between each other, there is an attraction force. If you have force with distance, you make energy. So interaction occurs only between polar molecules. So this is called dipole interaction. Okay, and then you have third one. You have fourth one, and you make something like this. But of course, you make it as a line, or you make it as a two-dimensional distribution. You make it as a three-dimensional distribution of the hydrochloride. You can make bonds. And this is called van der Waals bond. Easy, right? Easy. How about energy? When you want to think of energy, is that it's less than 5 kilojoule per mole. This energy is very less. The bonding is weak compared to the chemical bond. Secondary bond is always weak. It's kind of a proportion of this dipole energy of dipole interaction is a kind of a proportion of mu. Mu is dipole moment, and R is interpolar separation. Interpolar separation means this one. How far? If it's very close, energy is strong. That's for sure, right? That's for sure. If R is too far, energy is low. It makes sense. And as you know, temperature is what? This is bonding energy. This is thermal energy. Of course, bonding energy will against thermal energy. So temperature high, bonding energy will be low. I don't need you to remember this equation, but I want you to know the concept of this equation. For example, distance between here and temperature between here. So in Kahoot, I might say that, well, tell me the energy related to distance between molecules and also the temperatures of the environment, environmental temperature. The mu is Q times D. D is the dipole separation. Dipole separation means what? This is dipole between the intermolecular. It's intramolecular. Okay, dipole separation here. Mu is here. This is the dipole charge. How many charges? And D is the distance between here. R is distance between here. So I make the mark here for you. Again, I don't want you to remember this equation, but I want you to know the concepts. So when the temperature is low enough, so temperature very, very low, like very, 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 very low. So the thermal energy will not disrupt the bonds, and then they are forming by the dipole interaction. So the thermal energy low, the bonding, you can see bonding easily. So if the temperature low, that means the bonding, you can see the bonding and you can make it become solid, liquid or solid, right? So let me make example for you. This is hydrochloride, hydrochloride gas, hydrochloride liquid, hydrochloride solid, and aqueous hydrochloride solution. This is the one you always use. This is what we call 盐酸, right? In Chinese, 盐酸. Okay, so what's hydrochloride gas? At room temperature is hydrochloride gas. So when you open 盐酸 solution, you know the vapor come out. That's hydrochloride gas. Okay, be careful. Don't suck it. Okay, you have serious problem. You should, you know, you are chemical engineers. You know how to treat the chemicals. So if you reduce the temperature down to minus 85 Celsius, it becomes liquid. So liquid means what? Liquid means they are far away. And originally in gas, they are very far away. The molecule between each other, they're very, very far away. But if you reduce the temperature, they are closer. Because of what? Because this temperature, thermal energy is too low. There's no enough energy to pull this away. Okay, and the bonding, you can see the bonding you can see the bondings. So in the liquid, so it's the distance between chlorine molecules is closer. However, if you reduce the temperature down to 115 Celsius, minus 115 Celsius, and it becomes solid. So the thermal energy is low enough at the temperatures below this value is weak interactions dominates. Weak interaction between molecules means that dipole-dipole interaction dominates this situation. So this becomes solid hydrochloride. So they are much closer compared to the molecules are much closer compared to the liquid. Okay, so this time dipole-dipole force is greater than thermal force or thermal energy. Another case is hydrochloric acid. Hydrochloric acid is that you know, this hydrochloride will be taken apart. The hydrogen proton will take apart will join the water, right? This is different. Okay, when you see this is different compared to this and this and this. Okay, so this dipole-dipole interaction I just told you. Of course, you have attractive force and you have repulsive force. Right, so permanent dipole bonds is that the van der Waals forces exist between adjacent polar molecules, like as I just showed you, hydrochloride molecules. And associated bonding energies are significantly greater than the bonding involved induced dipole. So this kind of dipole, this kind of energy is energy of this kind of dipole and bonds is greater than induced dipole. What we are going to show you very soon. Okay, so these are the example of the dipole-dipole interaction. I just make a hydrochloride as a molecular as an example for you, and this is also, for example, polymer. Polymer is a kind of a long chain of the hydrocarbon, and this is hydrocarbon chain. Between hydrocarbon chain, these are chemical bonds, right? The chain here is chemical bonds, but between bonding, this chain and this chain is interaction. This is secondary bond. Right. I think I run out of my time today. I want to talk about this to you, but unfortunately, I don't have time. I will leave this for the next week. Okay, dipole-induced dipole interaction. Okay, so I think I better stop here today.